This video is sponsored by Magellan TV. Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. And I'm sure you've heard by now that the 2020 Nobel Prize in Physics was awarded to Sir Roger Penrose for his theoretical work on black holes, and to astronomers Andrea Ghez and Reinhard Genzel for discovering the supermassive black hole at the center of our galaxy. And this award is pretty consistent with the Nobel Academy's trend of splitting the prize up between theoretical and experimental sides of physics. It's also very cool that for the second year in a row, astrophysicists were included in the award. I'll be honest, my whole vibe toward the Nobel Prize is kind of mixed, because on the one hand, it is very prestigious, and it garners a lot of public interest, and it certainly recognizes individuals who made significant contributions to physics. But on the other hand, it's governed by some pretty outmoded rules, notably that the prize may only be awarded to no more than 3 people at a time, even though modern science is done as collaborations involving tens or even hundreds of scientists all working on the same project. And that may be why the prize didn't go to the Event Horizon Telescope team for producing the first direct image of a black hole. There's no question it's perhaps the most compelling observation ever made in astrophysics. But there's no way the Nobel Academy would award a prize to a team that large. However, that in no way should detract from the award going to Penrose, Ghez, and Genzel, because there's no question that they made huge contributions to our understanding of black holes. So I thought it would be fun to talk a little bit about the award today, and about the supermassive black hole at the center of our galaxy in particular. But first, I'd like to thank Magellan TV, who are very kindly sponsoring today's video. Magellan is a new documentary streaming service that dives deep into topics such as history, art, nature, and of course, space and science. In fact, while researching this video, I watched Monster Black Hole, which talks about how supermassive black holes are thought to form, how they drive the evolution of galaxies over time, and how researchers are recreating the conditions that form a black hole in computer simulations and even in particle accelerators. New programs are added weekly and can be watched on Roku, Amazon Fire TV, Apple TV, Google Play, and iOS. You can even cast directly from your phone to your TV. Best of all, Magellan has a special offer just for my viewers. By signing up at the link below, you'll get an extra month of Magellan TV absolutely free. Make sure to use the link in the description of this video. When Albert Einstein published his theory of general relativity in 1915, it was, to put it mildly, a revolution in how we perceive the universe. Time and space were no longer separate and absolute, but were woven together into a fabric of space-time. Matter and energy were no longer separate, but were equivalent and could be transformed into each other. And if that weren't weird enough, matter and energy can curve the fabric of space-time, creating the effect we call gravity. When Carl Schwarzschild solved Einstein's field equations, he showed that if space-time were to reach an infinite curvature, it would produce a singularity surrounded by an event horizon at a critical radius. Events inside this horizon were forever hidden from the rest of the universe because light could not escape from it. In other words, Schwarzschild came up with the first mathematical description of a black hole. When Einstein learned of Schwarzschild's work, he was surprised that his field equations could have such an exact solution. But he and others didn't think it was actually possible that matter could ever compress itself to such incredible densities. So black holes were regarded as more of a mathematical curiosity and not a real thing in nature. But in the 1960s, Roger Penrose and the late Stephen Hawking came up with a series of theorems that showed that once matter collapsed beyond its own event horizon, there was no force in nature that could prevent it from collapsing all the way down to a singularity. But Penrose went a step further. He showed how something that wasn't a black hole could transform itself into one by gravitational collapse, Along the way, he developed the mathematical tools to describe the behavior of light at all points in space and time inside the event horizon. He even came up with an elegant way to visualize the relationship between space, time, and light with his famous Penrose diagrams. Thanks to Penrose, I now know that if I were to extend my hand beyond the event horizon of a black hole, it would inexorably be pulled toward the singularity in the infinite future, even as the rest of me remains here in the present. There's other complications, such as whether or not I'm too busy being spaghettified and radiated to even notice, but Penrose showed that black holes can indeed exist in nature, and he's credited with making the most significant contributions to general relativity since Einstein himself. But as far as who actually discovered the first black hole, well, that's a different story. Cygnus X1 is widely accepted as the first black hole ever discovered. As its name implies, it's a strong X-ray source in the constellation Cygnus the Swan. It was discovered in 1964 in an X-ray survey of the sky. It was later shown to be a close binary system consisting of a blue supergiant star orbiting a black hole of about 15 solar masses. The X-rays are coming from an accretion disk of material that's being drawn from the star. As matter falls into the disk, it spirals inward and gets heated up to millions of degrees, producing X-rays in the process. Both objects in the SIG X1 system are too close together to be resolved in a telescope, so the mass of the black hole was determined by measuring the Doppler shift of the star's spectrum as it orbited around the source. Now, I don't know why the prize wasn't awarded for the discovery of SIG X1, but what I can say is that the discovery of the black hole at Sagittarius A star is widely considered to be the first empirical observations of a black hole. It was initially detected by Karl Jansky in 1931 as a strong radio source coming from the center of the Milky Way in the constellation Sagittarius. Later, it was dubbed Sagittarius A. Radio waves are very long, which means they are able to penetrate through the 26,000 light years of gas and dust between Earth and the center of the galaxy. However, their long wavelength also makes them hard to resolve the source into a single object with just one radio telescope. In 1974, Bruce Balick and Robert Brown studied Sagittarius A using the Green Bank Interferometer in West Virginia. This instrument consisted of 4 widely separated radio telescopes linked together through interferometry to produce a virtual telescope. They showed that Sagittarius A was actually several radio sources, with the brightest or loudest source at the very center of the galaxy. In 1982, Brown dubbed this object Sagittarius A star. Many astronomers suspected that Sag A star was probably a supermassive black hole. However, that's purely a speculative statement, and there were some competing ideas that Sag A star could instead be an ultra-dense cluster of neutron stars and white dwarfs instead of a black hole. And this was because nobody really knew its mass. But starting in the 1990s, large aperture optical telescopes started to become available. Now, viewing Sag A star at visible light wavelengths was still out of the question because the intervening dust generates 25 magnitudes of extinction. In other words, it reduces the otherwise visible light by a factor of around 9 billion. However, these telescopes were built in locations where infrared observations are possible. Now, since infrared waves are just long enough to avoid the dust, these telescopes were able to actually see the stars orbiting around Sagittarius A star. Now, let me just take a second here to say that we're actually able to see the individual stars orbiting a compact, unseen object 26,000 light years away at the very center of the galaxy. I mean, that still blows my mind. Anyway, with these direct images, it became possible to measure the orbits of these stars as they made their way around the black hole. By measuring their orbital periods, their distances from the black hole, and their orbital velocities, Astronomers could use these stars to weigh the mass of the object they were orbiting. The first astronomers to do this were Andreas Eckart and Reinhard Genzel using the New Technology Telescope at the La Silla Observatory in Chile. They calculated the mass of Sagittarius star as 2.45 million plus or minus 400,000 solar masses. Now, this was the first direct measurement of Sagittarius star's mass, and it's certainly hard to describe it as anything other than a black hole. But this was just one measurement and really needed confirmation before it could be considered valid. So Andrea Ghez and her team at UCLA used the 10-meter Keck telescopes at Mauna Kea to make their own observations from 1995 to 2007. Not only were the Keck telescopes much larger than the telescopes used previously, they were also equipped with adaptive optics systems. Adaptive optics uses lasers to create artificial stars that the system can then use to cancel out the turbulence of the atmosphere and produce ultra-sharp images. So for 12 years, Ghez and her team were able to make much more precise measurements of as many as 580 stars orbiting the black hole. These meticulous observations resulted in a mass of 4.5 million plus or minus 400,000 solar masses. This result sealed the deal. Sagittarius star was far too massive and too compact to be anything other than a black hole. Meanwhile, astronomers continue to make high-precision observations of Sagittarius star to test general relativity. In 2018, Genzel and his team used the Very Large Telescope to catch the star S2 as it made its closest approach to the black hole. To achieve the highest resolution possible, the team used all 4 of the 8-meter unit telescopes plus all 4 of the 1-meter auxiliary telescopes to create a ginormous 130-meter virtual telescope. These were incredibly difficult observations to make because the light from all 8 telescopes had to converge at exactly the same place at precisely the same time. But those observations showed that the light from S2 was being gravitationally redshifted as it worked its way out of the black hole's gravity well, thus confirming yet another prediction of Einstein's theory of general relativity. Then in April 2020, the Gravity team announced yet another confirmation of general relativity with Sagittarius star. By this time, the star S2 had been observed for its full 16-year orbit. S2's orbit precesses, meaning that the location of its closest approach to the black hole changes with each orbit. So the next orbit gets rotated ahead of the previous one, and the star traces out a rosette shape. Orbital precession can be caused by several factors, such as changing tidal forces on the orbiting object, quadrupole moments, and gravitational perturbations from, in this case, other stars orbiting around the black hole. But general relativity predicts that space-time itself can cause the orbit to precess as well. As the black hole rotates underneath the star, it drags the space-time around it in an effect called frame dragging. This adds yet another kick to the precession of S2's orbit. After 27 years of precise measurements, the Gravity team confirmed that S2's orbit precesses exactly as relativity predicts. Einstein was right yet again. Of course, nothing would be cooler than to actually see the black hole. Last year, the Event Horizon Telescope team blew our collective heads off when they revealed the first ever image of the black hole in the heart of the galaxy M87. EHT did observe Sagittarius star as well, but M87 is 6.5 billion solar masses, so it's 1,400 times larger than Sagittarius star. So even though M87 is 2,000 times farther away, both black holes appear roughly the same size on the sky. So why then haven't the team released an image of Sagittarius star? Well, the reason has to do with its comparatively small size. M87 star has a radius of about 127 astronomical units. That's a little less than the distance that Voyager 1 has traveled from the Sun. At that size, the signal from any fluctuation on one side of the black hole takes about a week to propagate to the other side. EHT's observations were taken only over the course of a few days, so that was enough to effectively get a still shot of the black hole. But Sag-A's star has a radius somewhere of around 30 million kilometers, or 0.2 astronomical units. And that's smaller than the orbit of Mercury. That means fluctuations happen on the timescales of just minutes, and that's too rapid for EHT to keep up with. That's not to say they aren't trying to tease out an image from all of that noisy data, but perhaps the next generation of EHT will have a better chance of getting it. But taking a step back, it is so cool to see the Nobel Prize went to Penrose, Ghez, and Genzel. And yes, I'm particularly keen about the two astrophysicists getting the nod because I remember a time when supermassive black holes weren't the widely accepted convention. Nowadays, we just take it for granted that they dominate the centers of galaxies and influence their evolution. Now, I've made a bunch of videos about black holes, including the gravitational wave signal of the most massive black hole merger ever detected. So please feel free to check that out when we're done here. As always, I'd like to thank my Patreon supporters for helping to keep Launchpad Astronomy going, and I'd like to thank Gary Tuhoy for becoming my newest supporter, along with Anna for her intergalactic level support, and Michael Dowling, Stephen J. Morgan, and Morrison Wild for their cosmological level support. If you'd like to support Launchpad Astronomy for the price of a cup of coffee every month, well, please make sure to check out my Patreon page. And if you'd like to join me on this journey through this incredible universe of ours, well, please make sure that you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay home, stay healthy, and stay curious, my friends.